Why, hello there, and welcome to Part 2 Mechanics 2.
Somebody tell me what that theme tune is in the comments, please.
It's our theme tune now, Connor.
No, it's not.
Right, the basics very quickly before we start. You just need to know that displacement is distance in a given direction. Speed is the change of distance per unit of time.
Scalar.
And velocity is the change of displacement per unit of time.
Vector.
So speed in a given direction.
Vector.
Obviously, you know that speed equals distance over time. You should know that. If you don't, please go away. I'm joking.
Kill
I love
yourself.
you. And therefore, the distance travelled is the speed multiplied by the time. I'm just rearranging that, which you will need to know. So, kicking off with that Babe Newton and his laws of motion.
I will just point out I'm seeing this image for the first time and I'm very disturbed because it looks like me.
His first law states that objects stay at rest or remain in uniform motion unless acted on by a force. Which basically means if you push an old lady out of a spaceship, she will continue to move at a constant velocity until acted on by another force.
Or until lack of pressure causes her blood to boil, her brain to explode, and her rectum to implode. Either way. Okay, moving on.
I haven't got an animation for that, Connor. Newton's second law is perhaps his most famous.
Is it now? I did not know this. Force is proportional to the mass multiplied by the acceleration. That's a nice little thing you need to know there, or as is widely known as the F equals ma formula. So a force, which he rather vainly named a Newton, really, subtle and humble man, is the amount of force needed to accelerate an object of mass 1 kilogram by an acceleration of 1 meters per second to minus meters per second squared.
Yeah, there we are, Connor. Newton's third law, which is, everyone forgets this one, is for every action there is an equal and opposite reaction. An example of this is trying to push your granddad over while sat on a wheelie chair.
I like my granddad.
You both move.
Whoa,
yeah,
animations.
You do. There we are.
We're being rather unkind to the elderly today, aren't we?
I'm just giving our animators a hard time with all this detailed OAP destructing animation.
Okay.
Yes.
I like the elderly, they're fine.
Yeah, thank you. Acceleration is defined as what, Connor?
As the change of velocity per unit of time.
Therefore, the unit is the metre per second or per metre or...
Right, so it's ms to the minus 2 if you're writing in a little, unit, or it's meters per second squared.
Or metres per second.
No.
Yeah, well, yeah.
Acceleration is a vector quantity with deceleration being shown by a negative value. To work out acceleration, you simply take the initial velocity of the and the final velocity and divide the answer by the time taken.
Simple, really. If you get given a velocity time graph, we'll come to these a little bit later, then the acceleration is just the gradient. And this is in the case of non-uniform acceleration. Maybe.
So it's a bit of curviness.
Yes. Yes. SUVAT.
Don't worry. You SUVAT. That was a really bad video.
There we go. Now you must know all about SUVAT. The set of 4 equations to help you find, well, SUVAT. Quick lowdown, Connor.
Well, S stands for displacement. I know it should be D, but meh, that would be distance.
U stands for initial velocity.
For some reason. V is final velocity. A is acceleration. And last but not least,
T is time.
Time Lord.
You see, there was a time gap between me saying that.
See?
That was a pun.
That was clever.
Now, using our acceleration equation, we can rearrange it for the first equation.
Don't ask me how.
Ta-da! Then, using a bit of maths and a touch of physics, we get our second equation, finding displacement.
That's creepy. Then, combining those, we get our third equation, the little red one there.
Then, using a little clever bit of maths,
Wait for it.
You can eliminate T, and voila!
More French. We have our fourth and final equation, the yellow one.
So, if you ever need to find any of those elements we mentioned, just use the WAHEY SUVAT equations of truth. Ta-da!
You know that they are given in the AQA formula booklet,
On to graphs.
That's just...
Distance displacement graphs. Mr. Connor Durkin, thank you, Mr. Connor Durkin, go.
That's okay. Let's start simple with distance time graphs, where the speed of the object will simply be the gradient of the line if it is straight. Let's get that correct. As the speed is constant. If it is changing speed, ergo acceleration or deceleration, then to find the speed at a point, draw a tangent to the line and find the gradient of that.
Mr. Connor Durkin, outwitting graphs since 2007.
That's a long time.
With displacement time graphs, it's the easiest way to deal with it. In your head, it's the swap distance for displacement and speed for velocity from what we literally just did. And that's your starting point. It's not exactly right, but that's... If you have no idea where to start, go with that in your head. The velocity at the point will again be the gradient, but be careful about positives and negatives. A favourite example is throwing a hamster in the air.
Is it?
The difference between the distance and displacement graphs is that as the hamster returns to the ground, the displacement from the start is 0, because if you looked away and looked back, the hamster hasn't actually moved. The distance, however, is high because from the hamster's point of view, well, he's been on a little journey.
He's going on an adventure.
I can fly!
No, he can't.
I'm a real boy!
He can fall with style.
With a speed time graph, the utility is that the area under the line, marked by this rather dashing shade of blue, will be the distance travelled.
Dashing. With velocity time graphs, somewhat helpfully, the area under the graph is the displacement of the object from its starting position.
Additionally, as acceleration is a vector quantity, as is velocity, handy that, the gradient of the line, in this case, is acceleration.
Right, let's use the hamster again.
I love the hamster, who we shall call Harold.
Harold.
Harold's velocity decreases from his initial positive velocity until he reaches the height of his little trip.
Yay!
Then he goes the other way, downwards, shown by the negative velocity.
Due to gravity.
The overall displacement again is 0, as the area is above and below the line. If you look at the velocity time, they cancel each other out because of the area, because it's a positive and then a negative, and so they kind of cancel out. If you do maths, bit of integration, cheeky integration. There we are.
Never again.
Or at least dear Harold landed where he started.
The gradient is constant, I hear you cry.
Well, yes, because the acceleration due to gravity acts on him the whole time in a negative fashion as he's going up and it's pulling him down, and that's
gravity,
it.
And gravity doesn't change, so it must be, constant.
Oh, sceptical accent for the win. Yeah, we are.
Accent.
Yeah, but what we were just
very well.
doing.
Now, admittedly, examples do have a tendency to ignore air resistance and any other resistance for that matter, but in this case it is rather important.
Drag acts on any fluid to counteract the force causing you to propel inadvertently
Nice word.
through the substance.
The drag increases until it is equal and opposite to the object's weight, where it attains terminal speed.
But if an object is moving in any other direction, drag will act on it in the opposite direction. So if it's moving left, drag will act on it to the right.
That's a complicated way of saying cars have limits too, which is probably why racing cars look so low and streamlined. Look at that.
This one.
Ooh, Red Bull.
I want to put a Red Bull in honey. What would that taste like?
Did
I just say a Red Bull? That's
a
grammatically
Red Bull.
incorrect. Moving on to projectiles.
Like
the
bullets.
key to projectiles is simply that objects involved have separate components, horizontal and vertical ones.
Up and along, just for you.
The resultant force is seen in the path that the object takes, but by separating the forces into their components, everything gets a little bit simpler.
He said, but
In the classic example of lobbing a watermelon,
Classic.
or a melon,
in this case,
the vertical components will be affected by gravity.
gravity. When the melon is lobbed or thrown, think of the initial vertical component as 0 if you haven't fired it to the ground, only forwards. So you're not really going up or down, you're just firing straight along a horizontal axis.
Therefore, the melon is accelerated only by gravity, which explains the curve, because the melon is being constantly accelerated.
It's a nice little sort of thought experiment that, if you drop a bullet and fire a bullet at the same time, they should hit the ground at the exact same time, ignoring air resistance, because the only thing acting on them is gravity.
Yeah, and that is why the melon is doing that, really.
Projectile curve.
Horizontally, though, ignoring air resistance, there is no force to counterbalance the force of the melon being thrown, and so the component remains the same for the duration of the flight, the horizontal component.
Indeed.
All this means is that for the horizontal component, you only need to use speed equals distance over time.
STD or SDD.
But
DT.
Yeah, but for the vertical components, you will need the change in speed and everything like that. It means you will need to use
SUVAT.
Ta-da! The WAHEY SUVAT equations of truth.
Those 4 little ones there.
The most difficult examples is something being shot off an angle up off a cliff.
It's just harsh and mean.
Yeah, that's just mean. For example, using this example of a...
Look, it's an evil cliff.
Oh, I like that. I like this animation. Right. The easiest way to do any question like this is to split the problem up.
Splitty.
Firstly, the rise to the top, and then the normal parabola.
So to the height of the projectile curve.
Down to the earth. Sticking to the idea of splitting the resultant force into its components, you can again just use SUVAT for vertical and SDT, as Connor so lovely put it, for horizontal.
But in this example, your initial vertical component U will be something other than 0, but that is all.
Yes.
And what is this? Simples?
Yes, simples. It's really simple. Yeah, the meerkat. We love the meerkat.
I didn't design this, I'm sorry.
Energy now! Last little bit. It's quite a large bit, but it is the last bit. This kind of fits in with the topic, but hey, we don't write the spec, we just outrageously attempt to help the nation revise it.
Outrageously.
Energy, Connor. Brainstorm.
Well, you have potential, position, kinetic, motion, thermal, temperature, chemical/nuclear, reactionary, electrical, charge, and elastic, stored. All measured in joules, or J.
1 joule being equal to the energy needed to raise 1 Newton weight through a vertical height of 1 metre.
And also you need to know that energy cannot be created or destroyed. Again, this is the principle of the conservation of energy.
As it is in charge of all the pupil... Oh, shut up. I don't know.
He's been a long week.
I can't believe we got away with that
Barely.
twice.
Work is done on an object when a force acting on it makes it move. Pretty obviously.
The equation is work...
Work done.
Yes, go, Connor. I can't speak.
Is when work done equals the force multiplied by the distance it's moved in the direction of motion. If the force is acting not in the direction of motion, then again you have to use some trigonometry and some component forces up and along. Blah, blah,
You
blah.
get given a rather mean-looking equation for this, which simply takes the idea that we spoke about in our last video about the F cos theta component in our triangle of...
I would just point out it's supposed to be theta, the little angle, and he's written feta, as in feta cheese.
See, yeah, okay,
Feta
wow.
cheese. Oh,
If
I'm
the
hungry.
force is perpendicular to the motion, then the work done will be 0 because cos of 90 is 0. Hashtag WAHEY maths there.
Whoa, hashtag YOLO swag. Relentless plugs win, whatever that means. A little side note, on a force distance graph, the area under the line will be the work done. Isn't that useful?
Well, that's very handy, Connor. Thank you for telling me that. Kinetic energy now. Found with this equation. Boom! Half mv squared. Simply because the faster it moves, the more energy it has.
Ta-da!
Potential energy is the energy of an object due to its position. So, in human terms, if you were on a plane and you push that annoying kid kicking the back of your chair out the plane, then suddenly they have a lot of gravitational potential energy.
And a very angry parent next to you.
So, the equation for the change of gravitational potential energy is weight
MG.
multiplied by its change in height.
Angry parents.
Angry parents has got nothing to do with it. Mr. College,
Well, but lots of legal fees.
Some more work, energy and power. Energy can be
Lovely.
transferred in a range of ways.
And so some smart-ass decided to come up with a rate of transfer of energy. I give you, in the words of Jeremy Clarkson,
Power!
lovely.
Found using... This is... But if you didn't get that, that's the rate of transfer of energy.
It's called power.
Yeah.
Units watts, I believe. What is the unit of power? A.
I like it.
Our physics teacher is
Stop. Found using the change in energy over time or the change in the work done over time. Potato.
That's just, no, it's potato. Using what we know about work done, you can find the power output is just F times V, the output force and the speed or velocity of the object. Well, that was nice.
The output force and the... Yes, that was well done.
Yes, it was.
Yes, it was.
It was delicious.
And that, ladies and gentlemen, is it. That's part 2 mechanics. That's all mechanics. That's everything. If you listened to the last video, if you didn't, why haven't you listened to our last video yet?
Bye.
Bye. Bye.
I'm sorry.